Alright friends, we will now talk about some concepts of continuity, differentiability and smoothness. If you remember, when we wrote down the finite difference approximation to some differentials, we used the Taylor series expansion, and we said that that is possible when you have a smooth function and higher order derivatives exist. So the question is, can we quantify smoothness? Can we really say how smooth a function is? So that's one thing we want to talk about. So first I want to introduce the concept of an interval. So the open and closed intervals. So all of you are familiar with this, just a review. So we are going to talk about, let's say, a domain, let's say 0 to 1. This is just an example. And if I talk about the domain omega, which is 0 to 1, then this is a closed domain, and I put a bar on top of it just to show that 0 and 1 are included. So the boundary points are included. On the other hand, I could talk about an open interval wherein 0 and 1 are excluded. So 0 to 1 is just an example. This could very well have been A to B. And I can also generalize this in multiple dimensions. So if I talk about 2 dimensions, then I would be talking about omega is an area and the boundary is a curve. So if the curve is included, that's a closed domain. If the curve is excluded, then we are talking about an open domain. So this is just some notation. Okay, so we now are ready to talk about some elementary discussion on continuity, differentiability, and smoothness. So I'll begin with some definitions and then give you some examples to cement the idea. So definition number 1. A function f which is defined on omega and it's a real valued function. So I am talking about a function which is real valued and it is defined on this domain omega, and notice I have not put a bar on it, so it's an open domain. So it's an open interval, is said to be k times differentiable if its derivatives of order j, where j lies between 1 to k. In fact, I could even include 0 without differentiating it, the function itself exist and are continuous. Such a function is said to be of class C k. Okay. So what we are saying is that if I have a function which I can differentiate k times, and if the derivative, the existing derivative of course exists and it is continuous over this open interval omega, then I will claim it belongs to the class Ck. So if I give the example of, let us say, x square, y equal to x square on the interval 0 to 1, okay, the function itself is continuous, so definitely it is of the order C0 because the function is continuous. If I take its first derivative of x square, which is 2x, that is also continuous over 0 to 1, therefore that function is also of the class C1. If I take the second derivative, that would be simply 2, so that function is also continuous, so it is of the class C2. And I can keep on differentiating it. Of course, higher order derivatives are all 0, but they exist and they are continuous. So therefore, y equal to x square over the interval 0 to 1 is a C infinite function. Okay. So special case is a C infinite function where the function itself is continuous and all its derivatives, all the higher order derivatives, they exist and are continuous. Okay, so I gave you one example of such a function. Okay, the next definition is the following. So again a function, a real valued function f on domain omega is said to be of class CBK if it is Ck and is bounded that is I should be able to find a constant C for which fx is always less than this pre-assigned constant C, where C is a real constant, and this holds for all x that belongs to the domain omega. So clearly the example that I gave you, y equal to x square, is not only C infinite, but it is also a bounded function, and therefore it would be of the class CB infinite. So example, y equal to x square is CB infinite on 0 to 1, right. So I just wanted to make a note here that if the definition of Ck is on omega bar, then the distinction between Ck and Ckb disappears. Okay, so normally we talk about a closed interval, and then if you have a continuous function and k derivatives also being continuous, then it turns out that you can say it is also bounded. Okay. Now the reason we are doing this is because we will use certain interpolation functions to do finite elements, and these concepts will be useful. Okay, so we are going to use functions that are not going to be infinitely differentiable and infinitely continuous. Okay, so the functions themselves, for example, may be continuous, but their first derivative may not be continuous, and so on. So let me give you some examples. So let omega bar be given as 0 to 1 and omega is 0 to 1. So if I look at fx equal to 1, x, x square, x cube and so on, all these monomials, then these are C, B infinite. Okay, each of these functions I can differentiate them infinite number of times, and the resulting answer would be bounded as well as continuous over the interval 0 to 1. Okay. So that's one point. If I look at fx equal to 1 by x, again on the same interval 0 to 1. Now you will see that at x equal to 0 there is a problem. Okay. So, so this function is continuous, and so are all its derivatives, but it is not bounded. So therefore it is a C infinite function, but not C infinite B. Why is that? Well, I could draw y equal to 1 by x, with x, this is 0, this is 1, and at 1 of course I would get a value which is 1, but this function would look something like this, right? Of course I am only interested between 0 and 1. So you can give me a C, a constant C. Suppose this is the constant. I can always find a value of x where it exceeds this value of C. Okay. So anytime you give me that the function is less than a certain number C, I can always pull up a value closer to 0 which would exceed this value C. And therefore you cannot specify a bound a priori, and therefore this function is not bounded. But if you exclude this, then you know all the higher order derivatives, they exist and they are continuous between 0 and 1 if I exclude x equal to 0. Okay, so here is an example of a function which is C infinity but not C infinity B. Let's look at another function. So another example which is very typical of a finite element function. So let's look at this function, let's say between 0 and 1, and suppose it looks like this. So this is f of x. So let me define f of x as it is x for x less than equal to half, and it is half for x greater than half. So let's say this value is half. I'm sorry, the sketch is not to scale, but you get the idea. So clearly this is a continuous function. Okay, so it is also bounded because I can always specify a value, maybe a little bit more than a value of half, and the function is always less than that value. So it is definitely a C0 function and it is bounded. Okay. Now let's look at f prime x. So if I try to draw f prime x, then you will notice that from here to here I have a positive value, and then I have a 0 value in the rest of the domain. So clearly this value is 1 and this value is 0. So let me darken it a little bit. So now the first derivative exists, but it is not continuous. Okay. So therefore, this is a C0b function. So first derivative exists, but is not continuous. I'm sorry, yeah, C0b function. Okay. Let's talk about another concept. So we'll talk about something called Sobolev spaces. So let's define Sobolev spaces as spaces of the order K. So these are defined on the domain omega such that, so this is a space of all those functions W. Let's say W is a function of X such that W belongs to L2, W comma X belongs to L2, and so on, and W comma X, 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 K times also belongs to L2. So let me repeat. A function is of the order, or is of the, it belongs to the space Hk if the function itself is L2, its first derivative is L2, second derivative is L2, all the way to the kth derivative. We had talked about an L2 function in the last class, but let me repeat this for you, where L2 essentially defined over a domain omega implies that it is a function W such that if I carry out the integral over the domain 0 to 1, then the square is bounded. So it's a, so L2 is essentially square integrable. Okay. So Sobolev spaces consists of functions W. So Hk is a Sobolev space of functions W which have derivatives up to order K that are square integrable. Okay. So I hope the definition is clear. So this is just an introduction to a simple space denoted by Hk. So suppose I talk about H0. H0 means it consists of W, functions W, such that W belongs to L2. As simple as that. So I just need to take the function itself and make sure it is square integrable. If I talk about H1, then W as well as w comma x, the first derivative should belong to L2. Similarly, if I talk about H2, then w comma x and w comma xx, the second derivative must belong to L2. Now we'll try to make a connection between the ideas of smoothness defined by this integration process and the ideas which we defined a little bit earlier about the continuity and differentiability, and it turns out they are both related. So let's talk about that. Okay, so we have talked about Sobolev spaces. Some more interesting ideas. Suppose I have a space which is H k plus 1 and I have another space which is Hk, right? So the space Hk consists of all those functions which have first derivative is square integrable, the second derivative is square integrable, all the way up to the kth derivative, and of course the function itself is square integrable. Hk plus 1 has additionally, of course it has all the kth derivatives which are square integrable, but it additionally has the k plus 1 derivative also square integrable. So you can see very intuitively that this space must be a subset of Hk. In fact, that is what is true. So I am always going to have Hk plus 1 is a subset of Hk. So I have a pyramidal structure. So I start with a number of functions, okay. Maybe all of them are C0, it's possible. So they have all, so they are all square integrable. Then I look at some of these functions and their first derivatives are not square integrable. So I lose some of them. And then I go to the next level where I look at the second derivatives. Again, some of them which had first derivative was square integrable, the second derivative may not be. So I hope you are able to appreciate that as you get to a higher order Sobolev space, you have more constraints on the differentiability requirements of the function. Okay? We are saying that the higher order derivative, they exist and are square integrable. Let's look at some examples. Again, for simplicity, I will consider a space or a domain between 0 and 1. So let us look at a function w of x which is, let us say, simply 1 on omega. And I can talk about the function itself, is it square integrable? And you can very well see that w is definitely L2, because if I look at the integral 0 to 1 w square dx, that is actually simply 0 to 1 dx, and that is 1. So that exists. It is certainly less than infinity, which implies w is L2. What about w comma x? W comma x in this case is 0. So let us do that integral. So 0 to 1 w comma x whole square dx, and that will turn out to be 0 dx, which is 0. So certainly this is also less than infinity, so it also belongs to L2. And in fact, I can go on and on and on. So all my, they belong to L2. So therefore, this function wx equal to 1, it actually belongs to H infinity. Okay? Not just the function, but all its higher order derivatives, they are square integrable. Can I find a function which is not? So let me give you an example. that is not L2. Let me give you this function fx is x raised to the minus half on 0 to 1. So let's do this integral 0 to 1 fx whole square dx, and this turns out to be integral 0 to 1 x raised to minus 1 dx, and this is natural log of x between 0 and 1, and we have a problem here. So this is not bounded, right, which implies that fx does not belong to L2. Okay, so which actually implies that fx is not h0. Forget about h1 or h2 or h3. This is a function which is not even square integrable. Okay, but you look at the class of all monomials, for example 1, x, x square, x cube and so on, they are all L2, their higher order derivatives are also L2, so they belong to the class H infinite. Let me give you a preview of some of the finite element functions. So we are going to use in finite elements functions like this. So this is an example of a hat function. This is fx between 0 and 1, and for obvious reason it's called a hat function. Maybe I can call this value as 1. Okay, if you would like, we can say this value is at x equal to half. This function, as you can see, is a piecewise linear function. Is this function continuous? The answer is yes. It is continuous at all points. The left hand limit, the right hand limit, they are same at all points. Even at this point at x equal to half, if I approach it from the right or I approach it from the left, it's identical. So fx definitely belongs to the class C0. It is also bounded, so I can put a b here, it's a bounded function. Next I want to look at f prime x. So what about f prime x? And now you notice that this part of the function has a positive slope, this part has a negative slope, and there is a discontinuity at x equal to half. So the f prime x, if I may, between 0 and 1, it would look something like this. Okay, so it has a positive value and a negative value here and a discontinuity in between at x equal to half. So this is an example of a generalized step function. Clearly this function is not continuous. So it is continuous in this interval 0 to half. It is also continuous, I mean the open interval. If I exclude half, then it is continuous between 0 and half. Similarly, if I exclude half, it is continuous between half and 1. So at x equal to half, it is discontinuous. So therefore, f prime x is discontinuous, so fx is only C0, I cannot call it C1. And in fact, f double prime x is even more interesting. Notice this derivative is 0, the second derivative, this derivative would be 0, f double prime x, but I get a spike at x equal to half. So I can represent this in the following manner. This is x and this is a half, and I would get some kind of a spike here, right? So I can call this as the 0, 1, a generalized delta function. This is clearly not continuous. In fact, this function, therefore, the hat function would simply be C0b, and these are typically called as C0 functions. They are only continuous, their derivatives are actually discontinuous at some point, finite number of points in the domain. Alright, so what is the connection between the smoothness that we talked about in terms of continuity and differentiability in terms of C1, C2 or Ck versus the Sobolev space, which are Hk? So there is a theorem that connects them, and I would like to lay it out for you. So Sobolev theorem relates Hk to Ck. And how? It says that in one dimension, the space Hk plus 1 is actually a subset of Cbk. So it implies if a function is Hk plus 1, that means the k plus 1 derivative of the function is square integrable. Then it is actually Cbk. Okay. So this kind of relates the ideas of continuity from an integral point of view to the ideas of continuity from the ones that we are already familiar with. Okay. So when we want to look at a function being of the class Ck, we kind of inspect the function throughout the domain and look at its derivatives and continuity. On the other hand, when we look at a function belonging to the class Hk in the Sobolev space, we check its square integrability of the function and its derivative. And what this theorem tells us is that actually the two are related. Okay. So we will just use this as a model template, and of course in this course we will go back and forth discussing between the C space and the H space, and I hope you will be able to relate it to what we have just discussed. So I hope you are now able to appreciate the ideas of continuity and differentiability and smoothness. What we want to do next is look at the method itself. So here is what we will do in the next session. We will take a very simple problem, actually the Poisson's problem, and we are going to construct an approximate method to find the solution, or rather we are going to construct a method to find the approximate solution. And we will see how we can control the error. Okay. So we are going to choose a trial function, we will choose something called weight functions, and then we will design a method called the method of weighted residuals. And I will try to show you that by choosing different mechanisms of controlling the error, you can actually define different classes of methods. So hold on to that, we will do that in the next class. Thank you very much.